Welcome to this lecture on vectors, a geometric approach. We'll be looking at what are called vectors, which have both a number attached to them, a magnitude, and a direction. Examples for those are force, velocity, acceleration, others maybe pressure. Force, for example, it makes a difference if you push something to the right or if you push it forward. Velocity, it makes a difference if you're driving north or if you're driving east, each at 50 miles per hour, but you're going to arrive at different destinations. In contrast, there are also what are called scalars, such as mass and temperature. We can only assign them a number, but not a direction. I may have a mass of 90 kilograms, but it wouldn't make sense if I said I have a mass of 90 kilograms in a northern direction or a mass of 90 kilograms in a southern direction. I always have a mass 90 kilograms. Or temperature. Today's a really nice day on the Kenai. We have 70 degrees Fahrenheit in an eastern direction. I don't think you've ever heard that. You can only say, well, we have today 75 degrees Fahrenheit. No direction attached to it. In any case, here we do deal with vectors such as force and velocity, and let's get started. The first example that we have here is a boat crosses the river in the x direction at 12 miles per hour, and the current of the river is flowing in the y direction at 5.1 miles per hour. You could also say, well, the boat is going east and the current is going north, but either way. X and y components are always perpendicular to each other, so in order to figure out how fast the boat really is going with its own speed plus the speed of the current, we can use we should use the Pythagorean theorem, since, as I said, the two components are perpendicular to each other. So we plug these in here. The little gray bar that you see here, again, belongs to the equation editor. I actually can see all the symbols. Unfortunately, to you, it's just a gray bar. So here we add the squares of the two components, take the square root, and when I do that on the side, 12 squared is 144, plus 5.1 squared is roughly 26. I add those two, come up with 170, take the square root, roughly 13, and since we have two significant figures, that should be 13 miles per hour. The angle, since the angle is determined to the horizontal, and then we have the adjacent and the opposite, we would use the inverse tangent to determine that. The opposite would be the y component, so 5.1, and then divided by 12, and each of them are actually miles per hour, where the miles per hour are canceling. The opposite is smaller than the adjacent, so we should have an angle less than 45 degrees. I'm going to do that on the side. Inverse tangent of 5.1 over 12, come out with 23 degrees. And I'm going to double check that with the book, and those are the correct answers, respectively, if I actually find it in the book. Oop, never mind. I don't even have that in the book. Sorry. In any case, these are the correct answers. Next example. The other way around, when you have the vector given as well as the direction it's going. So a human cannonball might come out at a speed of 50 miles per hour at an angle of 60 degrees. By the way, in the meantime, I did find the example in the book, and that is correct, 23 degrees from the horizontal. The book actually lists 67 degrees from the vertical, which is the same. Okay. In order to get to this example here with the human cannonball, we have x and y components that we're supposed to determine. And since we have a vector at a certain angle, in order to determine the y component, which is the opposite, with the hypotenuse being given, well, we use the cosine. So we have 50 miles per hour times I think I have to borrow the times somewhere. Times sine of the angle 60 degrees. And of course, we know that sine 60 degrees is 0.866. We have that memorized. Times 50 comes out to 43.3, or simply 43. It looks like we have one or two significant figures. For the x component, well, we are determining the adjacent, and we have given the hypotenuse, so we're using the cosine. The cosine of 60 degrees, of course, is 1/2 times 50, comes out to 25. These two examples show that when we go from x and y components to vectors, we use the Pythagorean to get the length of the vector, and we use the inverse tangent to get the direction, the angle. When you go the other way around, where we have given the vector, and then we want to figure out what the x and y components are, we use the cosine, because the x is usually the adjacent, and the y is usually the opposite, and that's where we use the sine. Okay, one more example. Here we add vectors. We actually had this kind of problem in the previous section, where the boat is traveling at an angle of 42 degrees from the vertical for 25 miles, and then it turns 90 degrees. So there's actually a right angle right here. But to the vertical, this one becomes an angle of 48 degrees, and it travels for 18 miles. And we're supposed to figure out how long is this total vector and at what angle. So we're going to determine the components of both of these vectors. And then what we do is we add the x components of the two vectors. And we would add the y components of the two vectors, but one of them goes down, which means we're going to subtract. And you're going to see that here, that we subtract the y components. Okay, let's look at how do we figure out the components. Well, the angle is given, the hypotenuse is given, and the adjacent in this case is actually the y component. So we're going to have here 25 miles per hour times, and let's see, I think I have to borrow a times again somewhere. 25 times cosine of 42 degrees. So this adjacent here is the y component of the vector c, where the hypotenuse is given and the angle of 42 degrees is given. And I'm going to come up with 25 times cosine of 42 degrees is 18.6. I'm going to save myself the units here because looks like I'm running out of space. The x component here would now be the opposite of the angle. So we have the hypotenuse, we have the angle. We're supposed to figure out the opposite, which is the x component in this case. So we use the sine. So it's 25 times sine of 42 degrees. And when I do that, I come up with 16.7 miles. Then the other vector, where we have given an angle of 48 degrees and the total length of the vector of 18 miles, we figure out what the adjacent is, which is the y component. So again, we're going to use the cosine. So we have 18 times cosine of 48. And I come up with 12.0 rounded. And then we do the opposite here, which is the x component, where we use the sine of the angle 48 degrees. So sine and 18. Yep, that's correct. And I come up with 13.4 miles rounded. Then we add the x components, so we're going to add 16.7 plus 13.4, and obviously we're coming up with 13.1 miles. Now I have space to put the units in. And then in the y component, the boat travels 18.6 miles, but then it actually travels back 12.0 miles. So we subtract the two, and we come up with 6.6 miles. And then now we have new x components. So we have an x component all the way here and a y component all the way here. And so we figure out what the total vector is. I'm just going to try to draw on the total vector. Well, never mind. Oops, now I totally messed it up. Okay, unfortunately Word doesn't allow me that very conveniently to draw something in here. So here's the total vector, and we figure it out by the Pythagorean, as we're supposed to do when we have components given to find the vector length we use the Pythagorean. So I plug these in: 30.1 squared plus 6.6 squared, and I do that on the side. 30.1 squared is roughly 900. 6.6 squared is probably roughly 40. Add those two, then square root of 940 is probably in the neighborhood of 30 or 31. 30.8 rounded is what I get, but it looks like we have two significant figures, so we probably should round to 31 miles, which is the same result that we got in the previous section. In order to figure out what the angle is, we have determined what the two components are, the x component and the y component. And so in order to determine what the angle is, we take the inverse tangent of the y component, 6.6 miles, divide by 30.1 miles, and I guess I'll leave out the units, save some space. Looks like a relatively small angle. The inverse tangent of 0.2, 12.4 degrees, or rounded to two significant figures, 12 degrees, which again corresponds to the result we got in the last section. And with that, we're concluding the lecture for vectors.